Guys, welcome to a tutorial on Pytorch. I'll be conducting a series of tutorials on Pytorch over the coming next few weeks. We'll be covering a lot of chapters related to Pytorch, chapters which are essentially fun to have a mastery over Pytorch, like tensors, autograd, automatic differentiation, schedulers, optimization, how to build models, and so on. And today we'll be taking the series 1 of this tutorial, or the chapter 1 of this tutorial. We'll be studying about tensors. But before getting into tensors and what tensors are, we'll be looking at a bit about PyTorch and what PyTorch is. So let's start. My aim here is to ensure that you guys get a full mastery over PyTorch. So let's start. Topics that we learn in today's tutorial. What is PyTorch? And we'll also be talking about the debate related to PyTorch versus TensorFlow. And then we'll be going on to cover the main topic of this tutorial, that is tensors. We'll be doing an interactive collab session. I will share the collab notebooks and the code with you so that you guys can do the code along with me. About me, you would be wondering what qualifications do I have to teach PyTorch. I'm currently a final year student at NSIT, and I've conducted AI research over 2 years at research labs in IIIT Delhi and NSIT, and I've published my work in several core A-star conferences like AAAI, EMNLP, ACLI, and so on. I also presented my work last year at a poster session in AAAI New York. And I've used PyTorch for all of my research projects, and I've just fallen in love with it. If you're a new student who's looking into getting into AI research, PyTorch or maybe TensorFlow is one of the tools that you should learn and master so that you can do well in your research career. That's also my aim of teaching you PyTorch. And years ago, when PyTorch wasn't so popular, uh, Facebook had conducted this PyTorch scholarship challenge along with Udacity, and I was one of the 300 students who was selected, and I was given specialized training on Udacity platform by the people who had designed PyTorch, and there were also a lot of curated assignments that I did. It was basically a nano degree that was given to me. And if you guys want to look at some of the work that I've done using PyTorch, most of it is in PyTorch. You can have a look at my GitHub or my portfolio. I'll share the links in the description. What are the prerequisites if someone wants to learn PyTorch? First is obviously the will to learn, right? You need to. Machine learning is a very daunting topic. If you're a student who's doing competitive programming or development, it does look a bit complicated. But if you have the will to learn, it's very easy. The rest is my work. The rest I have to teach you. You just need to have the will to learn. Second is a Google account because we'll be working on Collab, which is only accessible through a Google account. So you need to have a Google account. I assume you're having a working network connection if you're using this. And the fourth is that if you don't want to use Collab, that's fine. You can use the latest version of Python and pip. And if you're doing this tutorial on a local machine, I'll also guide you on how to set PyTorch, PyTorch up on your local machine. And not required for this tutorial, but do go through Andrew Ng's ML course. It contains all the basics that are needed to understand machine learning and deep learning. And there are a lot of concepts like um, gradient descent, differentiation chain. These are the concepts that you need to understand machine learning. And also in the future videos of PyTorch like autograd, automatic differentiation, I'll be not elaborating upon these concepts. I'll assume that you have learned them. So do go through this course. Now let's come to the main question. Okay, what is PyTorch? And PyTorch is very simply an open source machine learning library which is designed to build and deploy machine learning models. And it has been developed by research scientists at Facebook AI Research, and it is it is hugely popular right now in research and industry. In fact, most of the research projects that I see coming from colleges and industry A lot of them use PyTorch code. So hugely popular and in-demand library, and must learn if you want to delve into deep learning, because you can't build networks using NumPy or other scientific libraries. You can do it using TensorFlow, but we'll be talking about the differences in the next slide. Uh, if you look at the open source projects which are using it, some of them include Hugging Face, Flare, and OpenMind, popular open source projects which are using PyTorch. So if you want to contribute to these, you need to know how PyTorch works and what are the functionalities that PyTorch offers and how to use them. It is also used by popular companies like Tesla and Facebook. And Tesla uses PyTorch entirely for its autopilot functionality in the Tesla cars. And if you don't want to learn PyTorch, that's fine. There's some other alternatives also, like TensorFlow, Theano, Scikit-learn. But with the exception of TensorFlow, others do not provide the kind of functionality, the kind of flexibility, the kind of features that PyTorch provides. So it's either PyTorch or TensorFlow. Now, okay, now you have come to the main debate question, which is there that what should I learn? Should I learn PyTorch or should I learn TensorFlow? Now, I started 3 years ago when I started with machine learning in 2018. PyTorch wasn't very popular. TensorFlow was popular, but it was very difficult to use, and we'll go through why that was in this slide. TensorFlow is based on this concept of a static graph. So if you have studied about machine learning, what you do essentially is that you build a model, a mathematical model, which maps your input to your output. And our objective is to train this mathematical model and optimize it so that it gives the right outputs for the correct inputs. Uh, in order to train that model, your machine learning libraries represent this model in the form of a graph. So basic operations like multiplication will be represented as a node, addition will be represented as a node, and so on. And we'll be talking about that in the next tutorial in AutoGrad. But just assume that for now we represent a mathematical model in the form of a graph. What TensorFlow does is that it represents it in the form of a static graph, which means that once you have defined your graph and once you cannot make any changes to it. Okay, the only time you can make your changes is when you start a session and you run your model. You can make changes to your weights, and you can make changes to model weights, bias weights, and so on. You cannot make changes to the graphical structure. After that, when the session is over, you have a static model with you. You cannot make any other change. This is a very difficult concept, especially if you are a machine learning researcher. For example, you want to change the structure of the machine learning model mid-training to see what happens. You can't use TensorFlow for that. So PyTorch, on the other hand, uses this dynamic graph. Uh, it builds a dynamic graph, which means that even in training, you can change your graph structure. You can change how operations are done, and it will adjust to it. This is one of the main differences between PyTorch and TensorFlow. The other is the concept of data parallelism, which means that if you have multiple GPUs with you, you can distribute your data amongst these multiple GPUs. PyTorch provides a ready API called torch.nn.dataparallel for multiple GPUs. You can do this in TensorFlow, but it is a bit difficult. There is no such API for it. Uh, so PyTorch wins in this regard. Now, you might want to deploy your application or your model for real world applications. In this regard, TensorFlow is ahead by light years of PyTorch. It provides something called as TensorFlow serving, which means that you can serve your models on the cloud in the form of API. And it's a very easy process, very easy to do, and you can serve your model as an API without any such external, without using any external background framework. In case of PyTorch, you might have to use something like Flask or Django, and then wrap your model around it and then serve it on the web, which can be done, but it is not very easy as compared to using TensorFlow serving. Now, other things again, when we talked about TensorFlow, we talked about static graph, we talked about creating a session and running the graph in that session. Now Python doesn't work like that. Okay, Python just take you start with your code and you run your code, and there is no sessions or anything. So when you code in PyTorch, it inherently feels like you're coding in a Python environment. While TensorFlow for me initially was like coding, in a compiler language. It was very difficult. The other is that PyTorch and TensorFlow have this library versus framework dynamic, where TensorFlow provides certain helper functions for you and to help you train the model, but PyTorch has this entire suite of libraries which will do everything from loading your data to training your data to inference, everything. It has these different libraries like Torch NLP, Torch Audio, Torch Vision for all different kinds of data that a user might process, which is a really good thing because then it becomes a framework, right? You can use it to do any task in machine learning. That is also very beneficial in PyTorch. Okay, thanks guys for listening through these initial slides. Now we'll be moving on to our tutorial of Tensors and Collab, and we'll be doing a code along. Collab is a great tool that I'll talk about now. Thank guys. Topic that is there in this video, which I'm going to teach you, that is Tensors. Let me tell you about a cool tool that Google has developed so that basic machine learning uh, learners like you or me could do machine learning and deep learning at ease. This tool is called Colab, and Colab has been developed by Google, and you can compare it to a Jupyter notebook that is hosted on the cloud. It is very, very beneficial. It provides hardware accelerators like GPU and TPU. If you have a Google account, you can easily go to Colab and log in through a Google account. If you want to code along with me, you can click on new notebook. A new notebook will be created for you. Otherwise, I have created a notebook here, which I will share it with you guys. The link will be in the description, and we'll go through this notebook and we'll try to understand what tensors are and write some code and read some code to understand what basically tensors are. Initially, if you want to use the GPU runtime here, you need to go to runtime and you need to change your runtime type. I've already used the GPU here while I was creating this notebook, but you will have to select GPU here, then you will have to save. After you save, you need to connect to their cloud. So automatically connect, or you can also connect to a local runtime, whatever you want. Uh, they provide a lot of flexibility with it. Once you get a green tick here, you know that you have been connected, and this will show your RAM and disk usage, how much RAM is being used, how much disk is being used. Now we learn about some basic blocks of PyTorch, and two of the basic blocks are tensors and automatic differentiation. In this video, we'll talk about mainly tensors. Now, basic understanding of these concepts is very required if you want to master PyTorch. And a lot of people just jump into PyTorch, and I did that 3 years ago, and becomes very difficult. Now, uh, it becomes very difficult to get that kind of expertise over PyTorch. So I am there to teach you these two concepts. And first thing that you need to do with any Python library is that you need to install and import PyTorch. So thankfully Colab has pre-installed Torch in it, so you don't need to install it. But if you want to install it in your local runtime, or you want to install it in your local system, you should go to this link, and they have a very you need to select whatever is your system specification here, and you just run this command. So that's why I told you in the initial slide that you need to have the latest version of pip and Python. Now 1.9.0 is available, so you can just use this, type this in your terminal, or your command prompt, and you will have PyTorch on your system. But because we're using Collab, we don't need to do any of that. We just import Torch, and we import NumPy. NumPy is another mathematical library which is used for performing mathematical calculations in Python. Very useful and very helpful library. And if any of you guys have done some machine learning courses, definitely you would have come across NumPy and Pandas. Uh, okay, let's discuss what tensors are. First, let's import this. Now let's discuss what tensors are. Okay, tensors are very similar to matrices or arrays that we see. So a 2D matrix can be called a tensor. A 3D array can also be called a tensor. And in machine learning, if you have done, for example, and-to-ng course, all the inputs, weights, outputs, everything is represented in the form of these matrices. And these matrices constitutes tensors. Now, Torch provides an API to define tensors known as torch.tensor, and it's in fact extension of another API provided by NumPy called numpy.ndarray, which is again a method to convert your matrices into NumPy arrays. And the difference between these two APIs is that the API provided by Torch enables you to perform automatic differentiation, autograd, and also supports parallelization and GPU operations. So it's very essential for machine learning, having the torch.tensor API. And there are a lot of subtopics within tensors that we're going to talk about. First we're going to talk about how tensors can be created, how can they be initialized. Then we're going to talk about what tensor attributes are, what tensor metadata is, and how can we store these tensors in physical memory. So when we progress from attributes and metadata to storing tensors, we'll try to see how tensors, this concept called stride, which is used, to store tensors in physical memory. After that, we'll see how what are the operations that are supported by PyTorch on tensors. Finally, we learn about this concept called Numpy Bridge, which is a very essential concept if you're using both NumPy arrays and Torch tensors. If you're switching between both of these, it's a very good concept that PyTorch creators have introduced. We'll be talking about that also. Let's start with the first subtopic. Now, initializing, as I told you before, that tensor is nothing but a version or a representation of a 2D, 3D, or n-dimensional matrix, right? It's nothing more than that. So we're using this 2D list as you see here as an input, and we are converting this into a torch.tensor. Uh, let's run this code block and see. So your input tensor in this case is uh, is given below, and whenever you will convert your input tensor into uh, torch.tensor, the tensor word will be appended to it. And if you want to check, you can also check the type of your tensor. Let's see, input tensor. So you see that your input tensor here is a torch.tensor. It's a good way to check the type that your uh, data structure is. Now this is one way. You can use your 2D list also. Now as I said, it's an extension over the torch.tensor is an extension over the numpy.nd array API. Now if you have a numpy array and you want to convert it into a torch tensor, very easy. You just pass that. Now we have taken this input from here, and we have converted into a numpy array. So numpy input is an numpy representation of this 2D list. Then we use uh, the dot from numpy functionality to create an input numpy tensor. And I'll soon be talking about numpy bridge here in the last, and we'll be discussing that both of these input numpy tensor and numpy input, both of them point to the same locations. So if you make any changes in numpy input, it will be reflected in input numpy tensor also. We'll talk about that in the end. Let's run this code block, and you'll see that it is input tensor from numpy. So you see that the tensor is appended here, and this one is not a tensor. Now you can also do other kind of initialization. So when you initialize weights, when you initialize biases, there are certain distributions that machine learning models follow. Some follow a uniform distribution, some follow a random distribution. In that case, you can use Torch has this inbuilt implementation. It's there in NumPy also. It is just an extension of the NumPy API to create zero vectors or to create random vectors. Now here the 2, 3 here represents the dimensions. 2 represents the x dimension, so we'll have 2x, 2 rows and 3 columns. Uh, Same goes for the random input. Now torch.rand basically gives you a uniform distribution over 0 to 1. Uh, that's how it has been defined internally. You can also change this by transformation. Doesn't have to be 0 to 1. Then you have the torch.ones. It creates a matrix with all ones. It's an identity matrix basically. Not an identity matrix. It creates a matrix with all ones. Let's run this code block, and you see that the zero tensor here all has zeros. This is a uniform distribution over 0 to 1, and this is a ones tensor with all ones. You have this, and these are the three main ways to create. If you're using some external libraries like Torch Vision or Torch NLP, in that case, the Torch.tensor will be automatically created from the dataset for you. In Torch Vision, for example, if you have an image, Torch Vision will do everything. It will take that image, process it, convert the 3D matrix that the image represents into a tensor itself. So you don't need to worry about it. Now, tensor just does not contain your 2D matrix. Okay, it also contains some attributes. It also contains some metadata regarding your tensor. It gives a lot of information about the tensor. When you perform these operations, this metadata is very important, and we'll discuss about these metadata in some details now. There are four main types of metadata or attribute that the Torch website talks about. So four of them are torch.deeptype, torch.device, torch.layout, and torch.shape. Torch.ttype essentially tells you what the data type of your tensor is. Is it a float? Is it an int? Is it a float in a 64-bit computer, or it's a 32-bit float? So on and so forth. So if you open this link, you'll see a lot of tensor attributes. What kind of data types are there? 32-bit, 14-point, 64-bit. There's a very very long list about them. And if whenever you want to define your uh, define your tensor, you can initialize the data type there itself. Now we have this random tensor that I have defined, rand input. Let's see what the d type and what the d type would be. The D type is torch.float32, which means that it's a float type with 32-bit. And you can also change this afterwards. Uh, Second metadata that is useful that is present in torch.tensor is torch.device, which essentially talks about where the device is residing. What happens is that sometimes we are using a lot of tensors, and some tensors are there on your GPU and some tensors are present on your CPU, and you're trying to do operations with both these tensors, and you get a error that they are not on the same machine or they are not on the same GPU. In that case, what do? You use you just do dot device. In this case, we know that it resides on the CPU because I haven't yet transferred it to the GPU. This portion of code allows us to transfer the input to a GPU. We'll talk about this later, what dot to means, but just assume for this moment that it transfers the entire array to the GPU. Let's run this. It usually takes some amount of time to transfer to the GPU. Now we have the answer that the new tensor now resides on CUDA with index 0. When you will check for dot device, so you will find that if it is a GPU, there'll be two attributes. First thing will be that there will be a type. Type will say whether it's a CUDA or a CPU. There'll be an index. So if you have multiple GPUs, it will also tell you which GPU your tensor is on. It's the first GPU. In this case, it's on the first GPU. And we can now see. Now, the second thing to understand is that this rand input that we have designed initially, which is in the CPU, will not be erased. What you will get is that this entire code will be copied to the GPU, but it will not be erased. So if you're a very memory conscious or very you don't want to, you just want to you want to save any inch of memory, you will need to delete this rand input afterwards. As we run here, we see that the old tensor is still there on the CPU. If rand input had been now changed to the GPU, we wouldn't have got this output. The fourth one, that fourth attribute which is very important, is torch.shape. It's very self-explanatory, not much to explain. It just tells you the shape of the tensor. In this case, it's 2 comma 3, and as you see, we defined it as 2 comma 3 here. Not much difficulty here. Now, this is a very important concept of strides in tensor storage that is there in Pytorch. Now, this is a concept that not a lot of people know. In fact, I didn't, when I started with Pytorch over 1 year, I didn't know what strides was. But if you are really focused on learning the essence of Pytorch, you need to learn what strides are and how strides help in memory representation of your tensor. How are tensors represented in the physical memory? Now we see that the stride of the current tensor, torch 2 comma 3, is 3 comma 1, and stride of the transpose tensor is 1 comma 3. Okay. Now just let me explain. We'll talk about physical memory, logical memory, and then we'll come back to this concept of strides. Okay, we have this tensor and we need to represent it in memory. We have this tensor and we need to represent it in memory. Now memory is not represented like this in the form of a 2D matrix. It's a continuous it contains a lot of continuous small memory locations where we need to fit our numbers. So we're assuming that in the physical representation you're using a 32-bit system, and each page or each memory location can only fit 32 bits in it. In that case, it can only fit one integer, and we are assuming that this array here is a torch.int32 type array. So in that case, every memory location will contain one number, and you can roll this entire matrix out and you can store it in your physical representation. So 1 will be stored in the first one, 2 will be stored in the second location, 3 will be stored in the third, and so on and so forth. You'll go and keep on storing. Now it's good. Now you have stored your logical representation, which you have, right? Which you are accessing, which you are seeing on the system. You've stored it in the physical memory. Now, how are you going to retrieve your data from this? Let's say that you want to retrieve. What do you want to retrieve? We want to retrieve your We want to retrieve 1 comma 0. In this case 1 comma 0, 1 comma 0 here is your 3, right? 1 and 0 here. Now how are you going to do that? Let's try to first code this up, and then we'll talk about how strides can be used to retrieve what is present at 1 comma 0. You can directly do this, right? You don't need to use two lines. Now I have defined it in the form of a tensor, the array that we had here, the 2D matrix that we had here. And let's look at the stride. What is the stride of this? Stride is a method, so you will have to use brackets. Stride here is 2 comma 1. Okay, let's note it down here. But the stride here is 2 comma 1. Let me bring this down. So I hope this is clear. Stride is 2 comma 1, as we saw in collab. Now how are you going to calculate 3? So what you do in this case is that you take this location and you do an element wise multiplication with the stride matrix. So how will this work out? Let's see. Let's calculate. Let's calculate. Okay. You do 2 into 1 plus 1 into 0, which you get as 2. Now you go and look at memory location number 2 and you'll find 3. So when you multiply your position that is there in the logical representation, you do an elementized multiplication with your strides, you will be able to find out your you'll be able to find out the location in the physical memory. So that's why strides are very useful if anyone wants to find out the location in physical memory. And in the back end, a lot of this process is abstracted, you don't know, but when it retrieves that particular number, it is going to multiply the strides with your location and retrieve the number from that location. Okay, now another concept which we'll talk about later is slicing, which we'll talk about after viewing all the tensor operations which are present. I hope that you have understood this. If you have any doubts, please mention in the comment section. Now, lot of options are there. Pytorch supported operations are there for on a tensor. You know, just millions of. There's a lot, not millions, lots of operations, hundreds and hundreds of operations which are there that you can perform a tensor. But we're going to talk about some main, and we just have a brief overview of some main operations which are there. So the first operation which is there is transferring tensor to a GPU. Uh, Earlier, you might have seen this this part where I had done dot to kuda here uh, when we were discussing about dot device metadata here. So in that case, we did dot to ensure that your this particular tensor is transferred to this GPU. Dot to ensures that your rand input is transferred to this GPU. Not really transferred, it clones rand input to this GPU, and we can test this. Now I have defined this particular tensor. It's a random tensor. The first integer which is there in a random tensor indicates your lower bound, and the second one indicates your upper bound. So the random tensor, works over the uniform distribution. In this case, a, u, a uniform distribution from 2 to 12 will be created with dimensions 3, 4, and we transfer this tensor to your first GPU. If you see in Colab, they only provide you with one GPU. You can verify this. As you see, there's only one GPU that's there, and some amount of memory has been used, which is obviously us transferring tensors there. And we'll see that again. It resides on that GPU. So if you want to transfer your tensor, use dot .2. Now another main operation which is there in NumPy is slicing. What is slicing? Slicing is essentially uh, cutting a portion of the array, cropping a portion of your array. In this case, what we are doing is that we are cropping it from 0 to 1, and we're cropping the y dimension from 0 to 1, and x dimension from 0 to 2. Uh, in the, we'll see that your tensor shape in that case changes. Now, in this case, what will happen is that it will not create new tensor. It will just create a view over the original tensor. If you make any changes to this array, it will be reflected here also. We also see that your shape changes. Whatever slice you have done, the same shape is reflected here. Another another major another major tensor operation which is there is concatenating your tensors. So in some cases, what happens is that you need to concatenate your tensors. If you have multiple models are producing outputs, and you need to concatenate outputs from all those models, you can use this toss.cat. We define three inputs here. We define three arrays. One is a random array, the second is a zero array, third is a one array, and then we concatenate those three arrays. Now, if you are one thing that you need to make sure is that the dimension that you are concatenating your array against, all dimensions other than that dimension need to remain same. So in this case, we are concatenating it against dimension 1. 3 remains the same. We can also change this. We can create a transpose array. And now as you said, the default dimension is 0. So in that case, everything other than 0 will be different. In this case, you'll see that it's a 2 comma 3 vector, it's a 5 comma 3, and so on and so forth. So every dimension other than your normal the dimension that you're concatenating against should remain same. Now a very important operation which is there in your tensors, multiplication. PyTorch provides support for this. Now there are two types of multiplication that you can do. Okay, uh, one is your element-wise multiplication, and your one is your dot product multiplication. Now, if you have done AndoNG's machine learning course, if you would have you would know what the differences between these are, but we'll go from the basics. We have designed a. I've initially defined a random array here, but let's define a one array and let's see what the results are in this case. Now, the array dimensions are 3 comma 3, and the array, this is the array result. Now, if you have done conventional matrix multiplication, this might seem a little bit suspect to you, because in that case what happens is that you will get a matrix of dimensions 1 comma 3. Now, my element wise multiplication doesn't work like that. What element wise multiplication does is that it will take one row of this matrix and it will multiply it with the row of this matrix. Let us say that we have a 2 comma 3 matrix. So this should match with your non-singleton dimension 0. How does this work? Let's just delve deep into this. We have these two matrices, okay? What In case of element wise, what happens is that one row of 1 comma 1 is multiplied with one row of 1 comma 1. In this case, 1 will be multiplied by 1, this one will be multiplied by this one will be multiplied by this one, and so on and so forth. But in case of, let's see what happens in case of dot product multiplication. Now, dot product multiplication is like normal multiplication only. Just as we saw, we get a torch tensor with the size 1 comma 3, but the row of this will be multiplied with the column of this, which is your normal multiplication that we see. Now, you can do these kind of operations with numpy arrays also. You can do these operations with you know, what you call lists also. Why do you need to use torch for it? So as I said earlier, the torch supports DP operations. So if one GPU will perform column row 1 with column 1, the second GPU will perform row 1 with column 2, and row 2 row 1 with column 3 will be performed by the last GPU, the third GPU. In this case, you will have all the three operations performed parallelly, and so time takes definitely very less in case of GPU, and everything will be taken care of by Pytorch. You don't need to worry about sending it to the GPUs and doing all that stuff. Everything will be taken care of by your Pytorch. So now we have understood what element wise and dot wise dot product multiplication are. The final operation which we'll talk about is the in place operations. Now, all the operations that we conducted here, are not in place operations. If you see, all of them are call by value techniques. In that case, what will happen is that a new tensor will be created. In that case, now you might want to, make sure that your memory, maybe your memory is less, and you don't want to create additional tensors. In that case, you could have in place operations. In case of in place operations, all the operations which are there, be it add, subtract, are all performed on the same tensor itself. So you don't need to worry about any extra memory that is being hogged by other tensors. You perform this in place operation. We define this in place tensor, and initially the current values of the same tensor are 6, but then we add 6 to all of these elements, and we see that the value of the same tensor is now 12. Now, as I said, it is a call by reference method. But the last topic which is there in tensors is Numpy Bridge, and it's not a very famous concept which is there. But if you are switching between NumPy and the arrays and torch.tensors, and both of them are referring to the same array, you have converted as I showed you initially, you've converted a NumPy array into a torch.tensor. In that case, you could use a bridge. Now what does bridge do? In case of bridge, what happens is that your NumPy array and your toss.tensor, both of them will point to the same memory locations. So if you make any changes in your NumPy array, it will be reflected in your toss tensor. If you make any changes in your toss tensor, it will be reflected in your NumPy array. Let's have a look at an example. I've created a zero array which is here, and I've created a zero array and I've created a NumPy array, which is basically a NumPy representation of that toss tensor. Now the original NumPy array we see uh, is your original NumPy array is, let's run this code block. So your original array obviously is a zero array. Then we add 1 to the toss tensor. Now let's have a look at what the NumPy array is. In this case, your NumPy array is 1. So you added 1 to the toss tensor, but the value in the NumPy array consecutively changed. So if you're switching between NumPy and toss tensor, if you're doing some panda operations or something else, you can use this NumPy bridge. It's very, very beneficial concept. Uh, So I hope you guys enjoyed, and I'll add all the links to the resources from which I studied and resources from which I'm teaching in the description. If you have any feedback or anything to say, please mention in the comments, because this is my first time putting out such a video, and I want to know what are the problems. If you're not able to understand anything, if I am slow, or if if I need to go into more detail, or if I need to be fast, just put it in the comment section. Feedback is necessary, and these are all the references. I will post everything on my website, and thank you guys.